People remember Albert Einstein for revolutionizing physics with his theory of relativity. But few know he once called one of his own ideas the biggest blunder of my life. That idea, the cosmological constant, a term he added to his equations to keep the universe static. Decades later, we discovered the universe was expanding all along. And that blunder suddenly looked a lot like prophecy. Today, dark energy, the mysterious force accelerating that expansion, is considered one of the great unsolved puzzles of science. But what if even that is wrong? Because now scientists have stumbled upon evidence suggesting that the cosmic expansion engine, fueled, we thought, by dark energy, has been behaving in a way our standard model never predicted. It's as if the universe's heart has been beating to a rhythm we didn't know existed. And just as researchers were grappling with this, the Webb telescope delivered another shockwave. Using its mighty golden eye, Webb spotted yet another early galaxy that should not exist. Not in our textbooks, not in our simulations, not in our wildest expectations. Somehow, less than 2 billion years after the Big Bang, a galaxy appeared that was already more massive than the Milky Way. If that sounds impossible, that's because, according to our established understanding of cosmic history, it is. Our models have always told us that in the early universe, galaxies were tiny baby-sized compared to the grand spirals we see today. They were messy, clumpy, and still finding their shape. And that made perfect sense. Galactic growth takes time. There simply shouldn't have been enough ordinary matter floating around back then to assemble something on the scale of our Milky Way. At least that's what we thought. But Webb keeps proving us wrong. Time and again, it's uncovered so-called universe breakers, fully formed massive galaxies appearing only a few 100 million years after the birth of the cosmos. Each one forces scientists to redraw the lines of what we thought was possible. And the list of cosmic curveballs just keeps getting longer. Now comes the biggest one yet. A galaxy so large, so unexpected, it has astronomers scratching their heads in disbelief. They've nicknamed it the Big Wheel. This monster existed only 2 billion years after the Big Bang, yet was already 5 times more massive than the Milky Way is today. That's not just big, it's absurd. Here's the twist. Researchers weren't even hunting for impossible galaxies when they found it. When they measured its redshift, the shock became real. The light from this galaxy had been traveling for 11.8 billion years to reach us, meaning it formed when the universe was just 15% of its current age. And there it was, huge, orderly, and ancient, quietly defying everything we thought we knew about the way galaxies grow. The discovery was officially christened the Big Wheel and announced in Nature Astronomy. The name fits. The galactic Ferris wheel stretches nearly 100,000 light-years across, making it about the same size as our own Milky Way. But here's the mystery. How on earth, or rather, how in the universe did it grow so massive so quickly? Webb's data didn't just reveal its size. It also gave astronomers a peek at how this giant spins. And that's where things got even stranger. The Big Wheel's rotation speed perfectly follows the Tully-Fisher relation, a rule that links a galaxy's spin to its brightness, which in turn reveals its mass and distance. Translation: the Big Wheel isn't just big, it's stuffed with stars, making it one of the most star-rich galaxies ever found from such an early chapter of the cosmos. Even more shocking, its elegant spiral arms and balanced structure match the largest and most mature galaxies we see today. Despite forming when the universe was still young, our models say spiral galaxies are patient builders. They grow over billions of years, feeding on a steady trickle of gas from surrounding star clusters. But those mergers usually scar their shapes, twisting their graceful spirals into messy, chaotic blobs. That's why the Big Wheel is such a cosmic paradox. It's huge. It's ancient. And it's still perfectly symmetrical. Adding to the puzzle, its growth rate is normal. Not supercharged, not freakishly fast, just ordinary. That shouldn't be enough to make a galaxy this gigantic so early in the universe's history. So, how did it pull it off? The answer, astronomers believe, lies in its cosmic neighborhood. The Big Wheel lives in a patch of space where galaxy density is 10 times higher than average, a bustling intergalactic city compared to the quiet suburbs of space. This crowded environment may have led to a series of unusually gentle mergers where incoming galaxies slipped into the spiral without tearing it apart. On top of that, Any gas flowing in from the surrounding area seems to have synced perfectly with the galaxy's rotation, letting it expand rapidly without losing its elegant shape. In short, the big wheel won the cosmic lottery, born in the right place at exactly the right time. And luck played a role for us, too. Finding such a galaxy was a statistical miracle. Based on our current models, the odds of spotting a big wheel air-type galaxy in a survey are less than 2%. The only reason we found it may be because it happened to sit in an unusually dense and distinctive part of the cosmos. But this is where things turn from intriguing to unsettling. The rapid, orderly growth of early galaxies like the Big Wheel isn't just a quirky footnote. It's a red flag. Because while it challenges galaxy formation models on a small scale, it also hints at something far bigger: cracks in the very foundations of cosmology. A new wave of analysis is suggesting that one of the core pillars of our understanding of the universe may be about to crumble, and that our standard model of cosmology could soon be relegated to the history books. To grasp why astronomers are now whispering about the end of our cosmic playbook, we need to rewind to the very nature of the universe itself. The cosmos isn't a still, frozen stage. It's a living, stretching fabric that's been expanding ever since its birth 13.8 billion years ago. For most of the 20th century, scientists assumed this expansion would gradually slow down under the pull of gravity, like a ball tossed into the air, inevitably falling back to Earth. Then came the 1990s, and with them one of the most jaw-dropping surprises in modern science. Instead of slowing down, the expansion was speeding up. An unseen, inexplicable force was pushing the universe apart faster and faster. That mysterious something was christened dark energy. Here's the problem: we've never actually seen dark energy. It's an invisible placeholder in our equations, a theoretical ghost that makes the math work. The standard model of cosmology, grounded in Einstein's relativity, assumes this dark energy has a constant density everywhere at all times, a steady, unchanging cosmic pressure inflating space itself. At least, that's what we thought. In recent years, cracks have begun to form in that certainty. One crack is the infamous Hubble tension, the fact that no matter how you measure it, the universe is expanding faster than our models say it should. Another, even more unsettling, is fresh evidence suggesting dark energy itself may be changing. Last year, astronomers added fuel to the fire with results from DESI, the Dark Energy Spectroscopic Instrument, a cutting-edge project in Arizona designed to map the structure of the cosmos with unprecedented precision. By charting over 15 million galaxies and quasars, DESI produced the largest 3D map of the universe ever made, double the size of anything before it. But DESI wasn't just measuring distances. It was also tracking delicate ripples in the cosmic web, ancient patterns called baryonic acoustic oscillations. These density waves were imprinted on the early universe when gravity and radiation battled for dominance, spacing out galaxies at regular intervals. By measuring these intervals across vast distances and different epochs, scientists can trace the history of cosmic expansion and the influence of dark energy over billions of years. That's when things got weird. The DESI data largely matched the standard model except when it came to dark energy. Instead of holding steady as our theories demand, it appears to have weakened over time. Cross-checking with other major datasets, supernova surveys, the cosmic microwave background, gravitational lensing only strengthened the signal. The deviation isn't just noise. Statistically, it's between 2.4 and 4.2 sigma. Not enough to call it a discovery yet, but enough to make cosmologists sit up straight. Mustafa Ishak Boushaki from the University of Texas at Dallas put it bluntly: "We are gradually heading toward the point of no return." Sisadri Nadatha of the University of Portsmouth was even more direct. "We now have multiple datasets all pointing in the same direction. The data suggest a changing dark energy with greater reliability than ever before. And if dark energy is changing, then the cosmological constant isn't constant at all, which means one of the key foundations of our understanding of the universe may soon join the growing list of beautiful theories that reality has shattered." Of course, we're not ready to declare the standard model dead just yet. The current statistical significance of DESI's results between 2.4 and 4.2 sigma is compelling. But in science, you need 5 sigma before you can call something a true discovery. Still, the findings are enough to send cosmologists back to the drawing board, questioning some of the most sacred assumptions about how the universe works. DESI director Michael Levi of Berkeley Lab summed it up best. Our results are fertile ground for our colleagues in theoretical physics, and we are excited to see what they uncover. Soon, we may get help from another eye on the cosmos, the European Space Agency's Euclid telescope, purpose-built to probe dark energy with unmatched precision. Its mission: to shine an even brighter light on this deepening mystery. And as Euclid sets its sights on the unknown, you can set yours right here. Hit that subscribe button, give this a thumbs up, and join us on this journey into the